Di nuovo, buon pomeriggio a tutti. Abbiamo il piacere di avere il professor Franco Iachello per le Majorana Lectures di quest'anno. Do la parola al nostro direttore di dipartimento per il benvenuto.
Grazie, senz'altro un grande onore e privilegio avere il professor Iachello qui in dipartimento per questa ormai tradizione consolidata negli anni di altissima qualità che è costituita dalle Majorana Lectures. Il professor Iachello non ha bisogno di presentazioni, vi ricordo che è italiano di nascita, siciliano, poi ha studiato in Italia, la sua formazione diciamo, accademica l'ha avuta innanzitutto in Italia, al Politecnico di Torino, poi è andato all'MIT dove ha conseguito il PhD, dopodiché ormai dalla fine degli anni 70 è professore alla Yale University, adesso è professore Gibbs di fisica e chimica. Il professor Iachello è una persona molto attiva e cosmopolita, sia dal punto di vista scientifico che dal punto di vista propriamente detto, nel senso che non è rimasto negli Stati Uniti nella sua torre d'avorio, se posso permettermi di dire, nel senso che ha continuato ad avere molto attivamente rapporti con i suoi colleghi italiani, anche napoletani, ma anche europei. Infatti tra l'altro è membro di diverse accademie scientifiche internazionali, ha ricevuto premi e onorificenze in tutto il mondo. È una persona che ho conosciuto personalmente qualche anno fa, quando ha collaborato con l'INFN ed io ero direttore dell'INFN. Insomma, è una persona che ci ispira fiducia e speranza nel futuro, nel senso che tra l'altro gli argomenti di cui si occupa sono argomenti attuali. Lui si è occupato di nuclei naturalmente, di struttura nucleare, di modelli, è famoso per questo, ma si occupa anche di fisica del neutrino, del doppio decadimento beta con e senza neutrini, e quindi questo, come sapete, è un argomento di grandissimo interesse per quanto riguarda la fisica attuale. E mi piace sottolineare questa comunanza di fisica nucleare, subnucleare e teorica, naturalmente, perché questo dimostra ancora una volta come in fondo la fisica sia una, ci siano tante sfaccettature, ma insomma le problematiche, la metodologia e soprattutto gli obiettivi sono gli stessi, cioè quello di un avanzamento della conoscenza. Io quindi sono molto contento, lo ringrazio a nome del Dipartimento di aver accettato questo invito e non vorrei prendere altro tempo, per cui dando il benvenuto a lui e a tutti i partecipanti, quindi un augurio di buon lavoro, lascio la parola al direttore di sezione, l'amico Giovanni Larana.
Allora, buongiorno a tutti, mi unisco le parole di Leonardo, è veramente un grande piacere e onore avere con noi appunto Franco Iachello. Chiaramente lo ringrazio moltissimo per aver accettato appunto di essere qui con noi in questa iniziativa, appunto come diceva Leonardo, molto importante, un'iniziativa annuale, la Majorana Lectures, che è organizzata dalla sezione INF di Napoli e dal Dipartimento di Fisica Ettore Pancini ed è curata appunto dai teorici qui di Napoli. Franco non ha bisogno di presentazioni, lo conosciamo tutti, è chiaro, anche perché Franco Iachello è da anni un riferimento per quanto riguarda appunto la ricerca nella fisica teorica, in particolare anche per quanto riguarda appunto le simmetrie, con appunto anche modelli importanti che sono stati sviluppati e applicazioni appunto su sistemi fisici. Quindi se uno volesse citare quello che è il più importante, che tutti riconosciamo, ma l'Interactive Boson Model, per esempio, è stato appunto molto importante, ma anche chiaramente appunto la dinamica delle asimmetrie appunto nei nuclei, anche il Vibron Model e così via. Quindi sono tutti achievements molto importanti che sono stati appunto una guida e un riferimento un po' per tutta la fisica teorica. Ma Franco ha avuto molti riconoscimenti, molti premi, appunto chiaramente sono molto numerosi, non mi soffermo ovviamente su questo, e ha avuto dei ruoli importantissimi in molte istituzioni. In qualità di direttore INFN vorrei citare il ruolo che ha avuto importante per INFN, cioè appunto in qualità di chairman appunto dell'advisory committee dei due laboratori nazionali di Catania e di Legnaro, ma anche chairman del comitato di coordinamento appunto dell'INFN, e attualmente appunto fa sempre parte del comitato di valutazione degli NFN. Quindi Franco è una guida, è stato ed è una guida, diciamo, per molti progetti degli NFN, e mi piace ricordare il progetto SPES, che appunto tutti voi conoscete, che attualmente è in una fase conclusiva di realizzazione, quindi sarà operativo poi nel 2019-2020, che ha avuto un forte supporto da Franco. Spesso ci siamo trovati anche a discutere appunto sia appunto di problemi della fisica di SPES e anche i problemi naturalmente più svariati di questa importante facility. È chiaro quindi che io a questo punto chiudo qua e vorrei augurare appunto a tutti un buon lavoro per il Majorana Lectures. Ringrazio ancora Franco appunto per essere qui con noi. Do la parola, penso forse Angela vuole dire qualcosa, oppure diciamo do la parola a Franco direttamente per iniziare appunto le lecture. Sì.
Diciamo, io ho preparato qualche nota, ma effettivamente sta già detto tutto rispetto a Franco. Io vorrei solamente aggiungere, diciamo, una nota personale, che Franco, diciamo, ha sicuramente contribuito al successo della conferenza che il gruppo di Napoli organizza, la International Spring Seminar, con la sua costante e attiva partecipazione dal 1987. Quindi passo ora la parola a Franco perché...
È un particolare piacere essere qui a Napoli per tenere queste lezioni Ettore Majorana. Ringrazio della presentazione che è stata fatta. Particolare piacere perché Ettore Majorana è stato professore qui a Napoli e Ettore Majorana è nato in un paesino a 10 km di distanza dal paesino in cui sono nato io, che è in provincia di Catania, è a circa 10 km, è nata a Militello, Majorana, e ha svolto i suoi primi studi infatti a Catania. Quindi particolare piacere per le lezioni Majorana. Anche l'università è intitolata a Federico II, un altro personaggio illustre del Medioevo siciliano, e quindi un particolare piacere per me fare queste lezioni. Le lezioni io le ho in inglese e se c'è qualcuno infatti nell'udienza che è in inglese, preferirei farle in inglese se possibile, va bene? Ecco. So the lectures will be 3 lectures, one today, one tomorrow, and one on Wednesday. The lecture number 1 will be on the general theory of double beta decay. Lecture number 2 will be on the nuclear physics aspects of this subject. Lecture number 3 will be on the atomic physics part of this subject. And then at the end we'll have some conclusion and discussions. I'll try to go very slowly. This is a very difficult subject. So to begin with, I'd like to start by reminding everyone that there are still many questions open in neutrino physics. Here are 3 of those questions. What is the absolute mass scale of neutrinos? Whether the neutrinos are Dirac or Majorana particles? And how many neutrino species are there? Either 3 or maybe more. And it turns out that an answer to these questions can be obtained by a process called neutrino-less double beta decay, which is usually abbreviated DBD. This is a process in which a nucleus X decays into nucleus Y with the emission of 2 electrons and no neutrinos. So I will start with an introduction about this process. So, as I said, double beta decay is a process in which some nucleus with mass number A and charge Z decays to a nucleus still with the same A, but with the Z plus or minus 2, by emitting 2 electrons or positrons, and in general also other light particles. In particular, here there could be other light particles. Now, In the case in which two neutrinos or antineutrinos are emitted, then here this process is usually denoted by two neutrino beta minus, or it could be that two positrons are emitted with here a neutrino, and this process will be denoted by two neutrinos beta plus. Now, these processes with emission of neutrinos and antineutrinos are predicted by the standard model. Indeed, this two neutrino double beta decay was suggested by Maria Gepeter-Mayer already in 1935, just a few months after the Fermi theory of beta decay had appeared in 1934. And for historical reasons, I'm going to show you 2 pages of the articles of Fermi, where unfortunately here the resolution is not good enough that you can read it. But the article is in German. It says there Versuch einer Theorie der Beta-Strahlen. And here is where Fermi introduces neutrinos. He says that some particles are emitted called neutrinos. Here is the word neutrino. And that is because already Pauli had suggested that in order to conserve energy and momentum in single beta decay, we need an additional particle. It's supposed to be very light, and that's the origin of this statement. I can read it to you in case you wish, but it's here about neutrinos. And later on, Fermi discusses the mass of neutrinos. And in this later page, here is a discussion of the mass des neutrino, the mass of neutrino, and he has here a picture which depicts what is supposed to happen if the neutrino has a mass. So if the neutrino has a mass, the end point of the Curie plot here for beta decay, for mass 0 should go down like this, but if the neutrino has a mass, since the mass will appear in the equation here for the energy and the momentum, mu is the mass of the neutrino, then the spectrum around the endpoint will be modified with m with the mass small. Here says mu kleiner. Here it goes like that. With the mu large, it goes like that. And so that is this is precisely what we use today to try to determine the mass of neutrino in direct measurements. Some of you may know that the experiment in Germany, in Karlsruhe, that tried to measure the end spectrum of tritium to determine the absolute value of the mass. The experiment is called Katrin, and it is essentially a repeat of this figure. Perhaps a comment is that it's going to be, unfortunately, very difficult with Katrin to detect masses of the order that we think the neutrino mass is today, which is a fraction of electron volt, because at that level there appear many other contributions to the end spectrum that Fermi, of course, at the time did not know. And if some of you is in Katrin, I'm willing to discuss eventually what are those modifications that are needed to extract the neutrino mass. So here again is the article of Maria Gepeter-Mayer called Double Beta Disintegration, where she introduces the idea of a possibility of measuring double beta decay with the emission of neutrinos. But she says the half-life for this process is going to be greater than 10 to the 17 years, which means that we cannot detect it, at least at the time in 1935, it was impossible to detect that process. And so it took more than 50 years to observe double beta decay. It was observed first by Elliott et al. In 1987, and the half-life that was measured for the double beta decay of molybdenum 100 is, as Maria Gepeter-Mayer already said, very large. In fact, it's about a factor of 100 longer than what she had predicted. She had predicted 10 to the 17, and was measured about 10 to the minus 19. We are going to come back to this because that's another major problem that we are going to see in neutrinoless double beta decay. Now, the double beta decay with emission of 2 neutrinos have been observed in 10 nuclei, and also the related process where positrons are emitted in barium 130 has been measured, just one nucleus. And all the measured half-lives are very long, going from 10 to the 18 to 10 to 21 years. And there is a review of all observed decays given by Alex Barabash. Now, those processes are allowed by the standard model, but the process where no neutrinos are emitted, which I'm going to denote by 0 nu beta minus, or 0 nu beta plus, or beta plus electron capture, or double electron capture, are forbidden by the standard model. And if observed, will provide evidence for physics beyond the standard model. In particular, will determine whether or not the neutrino is a Majorana particle, and will measure its average mass, as we will see in a little moment. But again, talking about history here for this process, and coming back to Majorana in 1937, in this article in Nuovo Cimento, suggested that neutral particles could be their own antiparticles. And Racah, the same issue of Nuovo Cimento, pointed out that the neutron cannot be its own antiparticle since it has a magnetic moment, while the neutrino could be such a particle. And here is, in fact, a copy of the Majorana article, which he called Teoria Simmetrica dell'elettrone e del positrone, where he makes a suggestion. This idea was trying to cure the problem with the negative energy solutions which appear in the Dirac theory of antiparticles, and was trying to cure that, and was suggesting that actually the antiparticle is a particle in its own, is not a negative energy state solution, and already says it here in Sunto, but also in the text where it discusses it. And here is a copy of the article of Racah in the same issue of Nuovo Cimento, 1937, also called Sulla simmetria tra particelle e antiparticelle. And Racah explicitly said, nella seconda parte si considera l'ipotesi che dovrà essere un giorno verificata sperimentalmente che nel caso particolare dei neutrini non si abbia una semplice simmetria, ma addirittura una identità fisica fra neutrini e antineutrini. So it's a completely different story, so that the antiparticle is its own particle. It's nothing to do, which happens to be, in the case of neutrino, identical with the particle. And then here at the end it says that this can happen for neutrini, può farsi per i neutrini, essa non sembra possibile per neutroni perché l'antineutrone dovrebbe differire dal neutrone e per il segno del momento magnetico e per la capacità di trasformarsi per processo beta in antiprotone. So it's very clearly said what is the situation there. So this occurs only for neutrinos and not for the neutron. So because of this now, major experimental effort started a few years ago to detect this process, neutrinoless double beta decay. And all experiments so far have given negative results, with the exception of an experiment by Klaptor in 2004. However, this result has been very recently completely disproved, and I'm going to come back to this point later on. Therefore, neutrinoless double beta decay remains one of the most fundamental problems in physics today over the world, and its detection will be crucial for understanding whatever physics beyond the standard model, and is currently the subject of many, many experiments. Now, in addition to in addition to the fact that the expected half-life is very long, another problem is that it occurs at the same time as the process with the two neutrinos. And so if we look at the summed energy of the two emitted electrons, the spectrum for two neutrinos is a continuous spectrum, which is like this, and the spectrum for neutrinoless double beta decay is just not continuous, it's just a line. And note that this has been multiplied by 10. So this is just a tiny bit here on the background of two neutrinos. This is another process that I will discuss later on. So in order to be able to extract the neutrino mass, therefore, or even to put a limit, one has to have a theory at the same time of 0 neutrino double beta and 2 neutrino double beta. We have to have simultaneously theory of both processes in order to be able to extract some information. Now, as a preview of what I'm going to discuss later on, we see that here, for all the processes allowed by the standard model, the half-life, to a good approximation, can be factorized. This is the inverse half-life, can be factorized into a phase space factor times the nuclear matrix elements, while for processes not allowed by the standard model, the half-lives can be factorized as the product of a phase space factor, nuclear matrix element, and the factor here, which depends on particle physics and on the models of neutrinos that we have in particle physics. This is true except for a process which is a double electron capture with 0 neutrinos, which is forbidden by energy and momentum conservation, but can occur only under conditions in which case the inverse half-life is a little more complicated. And I'm going to discuss this later on. So, for the processes then not allowed by the standard model, one needs to derive the function f coming from particle physics. For all processes, one needs the nuclear matrix elements. This will be discussed in lecture 2, and the phase space factors discussed in lecture 3. And for here, you see how complicated is this calculation, because lecture 1 will be particle physics, lecture 2 is nuclear physics, and lecture 3 is atomic physics, because the two electrons have to come out from inside the nucleus, and so we need to do an atomic physics calculation, which we have done, and so I'm going to show this to you. Okay, so this is the basic introduction. So let us now come to go more in detail into the theory of double beta decay. So let's start with the 0 neutrino double beta decay, where we have the process in which a nucleus X decays into nucleus Y and with emission of 2 electrons. And here is an example. The nucleus germanium-76 decays in selenium-76 by this process here. It can decay not only to the ground state, but also to some of the excited states of this panel nucleus. The reason why this can occur is because the intermediate of the nucleus, which here is arsenic-76, has an energy which is higher than this, and therefore the process of a successive two emissions of electron neutrino cannot occur, because this is just a virtual process, and so that's the reason why this process can occur. And once more, here is the half-life, or the inverse half-life. Phase space factor depends on atomic physics. Nuclear matrix elements depend on nuclear physics, and beyond the standard model depends on particle physics. Okay, so the first step is try to find what is the transition operator for this decay, and the 3 scenarios have been extensively considered. One is the case in which at this vertex here, the electron neutrino or antineutrino is emitted, And now if the antineutrino is the same particle as the neutrino, then it can be reabsorbed at the other nucleon with the emission of an electron. And now here is the case in which the neutrino is very light, like we suspect it is, that is with mass much, much smaller than some scale like MeV. But there is another possibility that there are neutrinos, very heavy neutrinos, in which case, again, we can emit the antineutrino here and absorb it there, but these neutrinos are much heavier, and I will discuss in detail models for these heavy neutrinos. And here is a third process in which some way here on the way between being emitted and being absorbed, the neutrino emits a scalar massless particle called a Majoron. Again, we are here with Tetra Majorana, and so this is the name was given in his honor. It's called the Majoran, this particle. Now, there are several formulations of this. In these lectures, I'm going to follow a formulation due to Fedor Sinkovich, which is the one that is currently adopted. So, how do we find an expression for this transition operator? Now, we start from the weak interaction Hamiltonian. Here's the lepton current, and here is the hadron current. And for the nuclear physics applications, this is the important part, what is the hadron current. And the nuclear current here is written in the following way. This is isospin operator that changes a proton into a neutron or a neutron into a proton. Then it has two pieces which were essentially already Fermi knew about these two pieces, a vector piece in which there is a coupling constant GV, then there is the axial vector piece, gamma mu, gamma 5, where is the axial vector piece, but there are two additional pieces which do not come in lowest order, come into next order, and so they are called higher order corrections. One is called weak magnetism, which has this structure of Q nu sigma mu nu, and then there is an induced pseudoscalar interaction with the Q mu gamma 5. The Q mu is the momentum transferred from hadrons to leptons. Also, we can consider right-handed couplings and other stuff and other processes, but for the moment, let's remain to this. So then from the weak interaction Hamiltonian, the weak current, we do a non-relativistic reduction and we go to the transition operator, T of P, which can be written and factorized in this form, some function H of P times physics beyond the standard model, which is indicated here by a function which depends on the mass of the neutrinos and the coupling of the neutrinos to the electron neutrino, because that's what we observe. So once we do this non-relativistic reduction, and I will write HP momentum space, in which there is now two isospin operators here, because we have a change of two protons into two neutrons or vice versa. Then there is a Fermi piece, there is a Gamow-Teller piece, which has this structure of sigma n, sigma 1 to sigma 2, and then there is an induced tensor piece, which is structure is that of the tensor interaction, which is written here. There are more elaborate formulations, but for the time being, we are going to use this one, which is the simplest formulation. Then each of these pieces gets contributions from vector-vector or axial-vector. These two are the main contributions, but also all these other terms which come from interferences between axial vector and pseudo scalar from weak magnetism and so on. So it's a rather complicated structure of the interaction that we have to deal with. Now, in front there are these form factors V, which can be split into a part called the neutrino potential and the part which is called the intrinsic form factors, whose expression is given here. You will have access to copies of my PDF files or my lecture notes, so you can find out in detail. I'm not going to spend too much time in giving all of this, but the two important pieces are the Fermi piece and the Gamow-Teller piece. The Gamow-Teller piece is the coupling constant GA, the axial vector coupling constant GA squared divided by this term, which has the axial mass, and then the vector part I've written in this form by putting in front GA, and then writing here as GV over GA, and then here as the vector mass. And then there are other terms which are induced combinations of the previous terms. Now, we also have to take into account the fact that the nucleon is not a point particle. It has a finite extent. The radius of the nucleon is about 0.8 Fermis, so it's not negligible. So we have to take into account then that effect. And so that means that the coupling constants will be momentum dependent. And again, GV for a free nucleon is 1, and GA for a free nucleon is 1.69. And the value of the vector mass can be obtained from electron scattering, and is this value. And for the axial mass, there are some uncertainties, but it's order of magnitude of 1 GeV. The induced high order corrections depend on the magnetic moment of the proton minus magnetic moment of the neutron, and here is some other structure that we have there. Also, we have to take into account the short range correlations, because the two nucleons cannot get too close to each other, and then this is done with introducing these Jastrow functions, which in configuration space has this expression here, and with values of these coefficients given there. And this will play an important role when we talk about heavy neutrinos or sterile neutrinos, as we'll see later. But for light neutrino is less of an importance. So finally, we have to compute the half-lives calculated usually in the closure approximation. This approximation is good for zero neutrinos, because the momentum of the virtual neutrino is of the order of 100 MeV over C, and the scale of the energy levels in the intermediate nucleus is about 1.1 MeV. So the closure approximation, which means summing all over the intermediate, the state's intermediate nucleus, is a good approximation. Here you see the energetics for this decay of germanium-76. The Q value is about 2 MeV. So this energy is about 2 MeV, and then here is the intermediate nucleus. Okay, for this lecture instead, the important part is what about this physics beyond the standard model? This is the important part in this lecture. So what is this function f? Okay, so we have three scenarios. One is the scenario with light neutrino exchange. You have to tell me about the time, how we are doing. How much time do we have for this lecture? 3:30. Okay. Okay. So we still have plenty of time. So I can slow down. Okay. Good. So now, first of all, light neutrino exchange. This function f happens to be proportional to the average mass of the neutrino. Average means that it's average with the matrix elements of the couplings between these light neutrinos and the electron neutrino. So this is a 3x3 matrix here, and I've written in this form not absolute value, because this matrix element may have a phase which may influence, in fact, this average mass. And And so that's the form, is proportional to the mass. And here we have put as a scale the electron mass just to have this quantity dimensionless here. And then the neutrino potential is this one. Why is this one? Now, neutrino is very light here, is essentially massless. So this neutrino potential is more like a Coulomb-like potential. The mass of neutrino is very light. And if you remember, the Fourier transform of the Coulomb potential is 1 over p squared. And so A is usually relatively small, so this potential is essentially 1 over p squared, which is the Fourier transform of the Coulomb potential. This comes from the non-relativistic reduction and of the interaction. So for a massless neutrino, for a neutrino with a very small mass, this neutrino potential is essentially Coulomb potential, which is very long range. So the neutrino or antineutrino is emitted at one end of the nucleus and is reabsorbed as possible, as far as possible, far away from that, at the other end of the nucleus. So for the light neutrinos. So very, very light neutrinos have these properties. So now you know that in the last few years, both a series of experiments for which the Nobel Prize 2015 was given to Art MacDonald, and so is a series of experiments on atmospheric, solar, reactor, and accelerator neutrinos have measured oscillations, and they provide information on light neutrino mass differences and their mixing. And the experiments provide these mass differences between the three neutrino species 1, 2, and 3. So they provide the experiment delta m squared and capital delta m squared. But the three neutrinos could be arranged, 2 are very light and 1 is a little bit heavier, or vice versa, 1 is very light and 2 are heavier. So this is called the normal hierarchy, and this is called the inverted hierarchy. Then we can evaluate what is the light neutrino mass, because what we do is we put it here as the mass of neutrino number 1, the mass of neutrino number 2, and the mass of neutrino number 3. But they are mixed, and the mixing angles are called here theta, and we can have either mixing of species 1 with species 3, or we can have mixing of 1 with 2, and which are the 2 here. And also there could be some phases for 2 relative to 1 and 3 relative to 1. So the information that we have on the masses is that M1, 2, M2 can be rewritten in the following way as an average mass between 1 and 2 plus this delta m squared and capital delta m squared. So these 2 are measured experimentally, and they are given here. They are tiny, very, very small, while instead the angles now have also been measured. Until 2 years ago, the only angles that they were measured with some accuracy were theta 1,2 and theta 2,3. But 2 years ago, an experiment, or 3 years ago, an experiment at Daya Bay has been able to measure the angle theta 1,3 very accurately, and therefore now we have also an accurate value for theta 1,3. And so we can have a prediction now based on these measurements on what should be the average mass. This fit that this year was done by Gianluigi Fogli and Eligio Lisi and others in Bari. So it is the latest fit to all the oscillation parameters that we have at the moment. But now, based then on the oscillation experiments, we can now predict what we expect to see. Now, we cannot predict precisely what are the values because there is, first of all, an uncertainty in the experiment, but also there are those phases, phi 2 and phi 3, that we don't know so far, have not been measured, and it's going to be extremely difficult to measure them. Eventually they will, but at the moment, still we don't know precisely what are the values of those phases. And so we plot here the situation by plotting the average neutrino mass in electron volts versus the lightest neutrino mass, again, in electron volts. And so the spread here is due to the fact that we are varying the phases from 0 to 2 pi. And is divided into inverted hierarchy and normal hierarchy. This is the holy grail of this field. This picture is the holy grail of this field, and is the picture that tells us what we expect from this situation. The original figure was done by Francesco Vissani at the Gran Sasso, and is sometimes called the Vissani-Strumia plot for this figure here. But this is what we'd expect. First of all, you see that we have a region here on the left-hand side where the inverted expected mass ranges from about 50-60 milli electron volts into about 20 milli electron volts. And then we have here the normal one, which ranges from few milli electron volts to about 2 milli electron volts for the normal one. But now it could be that all three neutrinos, although their mass difference is small, but nonetheless they are about degenerate. So there is a region here called the degenerate region where the three neutrinos have all of them a relatively large mass, but that this large mass, but they are essentially degenerate. The splittings are very small. We have measured the splittings, we don't know what is the mass. However, in recent years now, the cosmologists have tried to attempt to give a limit on the number of neutrinos that we have and on their mass. And so this is called cosmological bound. And this cosmological bound gives a bound on the sum of the masses. So the sum of the masses in 2008 was expected to be 0.6 electron volts. And now there is a new measurements from Planck, which to 68% confidence levels gives a bound of 0.2 electron volts. So these bounds now are indicated in this plot. And you see now that we are stuck into a cage because we have to be into this region here. Now, of course, there are several people who are not completely confident with the cosmological bound because it's obtained by a very complicated fit to data. But nonetheless, this is something that we have to keep in mind, that we may be bound by the results of cosmology, and that this bound seems to be very stringent because the sum of the masses 0.2 means that each individual mass, if we assume that is 1/3 of that, is going to be 50 milli electron volts, which is very, very small. So this is something that now the people who do double decay have to worry because of cosmological bound. Also, the cosmological bound says that there are, the bound of the species of neutrinos is 3.05. Again, only 3 neutrinos. We'll come back to that later on. Okay, so that's the scenario for light neutrino exchange. what about heavy neutrino exchange? What about if there are neutrinos that are very heavy, but they are very weakly coupled to the electron neutrino? So what happens is if you derive the theory and you do all this non-relativistic derivation, now the transition operator becomes some functions HP. I put an H because this function is for heavy, which is different from the one before. And also F depends on the masses of the heavy neutrinos and the masses and the couplings of the heavy neutrino to the electron neutrino. And in this case, if you do the derivation, you find that this function F is inversely proportional to the mass of the neutrino. And to put a scale here, this time I put a proton mass for scale, not an electron mass, but it's inversely proportional. And so here is the expression for this. So the masses now appear not in the numerator, but in the denominator. So, so that's the main difference, is that now we are sensitive to the inverse mass of the heavy neutrino. And also the neutrino potential is different, because now if the neutrino is very heavy, it's a short-range interaction. And so here the neutrino potential is a constant. Okay? It's just a constant because it's a short-range interaction. A constant means a contact interaction. So the Fourier transform of the potential is a constant which has been normalized in some fashion. So here is then a difference. Now, what about bounds on the masses of heavy neutrinos? Now, this unfortunately are model dependent. There is a suggestion by Francesco Vissani together with others that from lepton flavor violating processes and other possible experiments at LAC, we can put a bound on this F, because F can be written as the ratio of the mass of the W boson over a hypothetical W right boson, which here in this calculation I put a 3 at TeV, but we don't know if it is there or not, but it's a hypothetical. The mass of the W boson is 80 GeV, and so, and then there is this part here, and so this quantity eta is called the lepton violating parameter, because this process then violates lepton number, and the constraints on eta can be converted into constraints on the heavy neutrino mass by just a simple formula here. But now if both light and heavy neutrino exchange contribute, then the half-life will be written in this form, and now the two contributions could add or subtract depending on the relative phase. So there could be an enhancement if both contributions are of the same order of magnitude and they add constructively. So that's something that again we have to keep in mind. Now let us analyze the other one of the other possible processes, which is the emission of a massless scalar particle. I'm going to denote this scenario as 0 nu beta beta m. This scenario was very much of interest in the 1980s. It was studied by Germini, Roncadelli in an article in the 1980s, but especially by Georgi, Howard Georgi, and Sid Glashow and Nustinov also studied this process. And they were introduced as massless number Boston bosons, which arise from a global baryon number minus lepton number symmetry, which is broken spontaneously in the low energy regime. And so they were introduced as that. The interest vanished because it was shown later that precise measurements of the width of the Z boson decay do not allow essentially this process to occur. But in the meantime, several other models have been proposed for emission of the scalar particles, which are called here chi0. It's an hypothetical particle, and here there is emission of a single chi0, and here is an emission of two chi0s, which could occur. So we have to calculate these processes as well. So there are many models that have been proposed, which are distinguished by whether this is an Ambu-Boston boson or not, what is the leptonic charge of the emitted majoron, and what is the so-called spectral index of the model. And you can see here there are many, many models that have been considered. I'm going to look only at some of these models. The transition operator for this scenario now can be split into this function HP, and the effective majoron coupling of the majoron, which plays here the role. This is the coupling of the majoron to the neutrinos or antineutrinos. And the inverse half-life for this process then is a phase space factor, which is different. So we have to do a different atomic physics calculation for this. The nuclear matrix elements, which are the same in this case, and this coupling constant. And of course, this is hypothetical, so we can put bounds, we can put limits on the values of this coupling constant if we wish. Okay. Now what? Light neutrinos. Majorana is much less the same. So only light neutrinos. So I'm now coming to the latest scenarios. So since we are not observing the process, everybody's now speculating on what could contribute to this. And so there are several speculations for the mixing of 1, 2, or 3 additional neutrinos, which I'm going to call number 4, number 5, and number 6, with masses in the electron volt GeV range. And these neutrinos are called sterile because since they have not seen so far, they must have a very tiny, very small mixing to the electron neutrinos. But actually, sterile neutrinos were introduced by Pontecorvo already in 1968, and they are defined as neutrinos with no standard model interactions. And in the last few years, in fact, several suggestions have been made for sterile neutrinos, either in the electron volt range of mass. In particular, Carlo Giunti and Marco Laveder have suggested that these neutrinos could resolve some of the anomalies that are observed for example, Borexino. Some of the anomalies that have been suggested which could be resolved by having sterile neutrinos in this range. I'm coming back to this later on to give you precise predictions for this, but for the time being, I'm just saying that there are possibilities in electron range. Then there are neutrinos in KV range, suggested especially in Japan by Asaka and also by Russian Misha Shaposhenkov. And then there are MEV, GV range, again, same people, and also by Visani and Tello and others for the TeV range. So the idea is to introduce these sterile neutrinos for solving the so-called anomalies in neutrino physics. For example, the reactor anomaly, where one observes coming from the reactor less neutrinos than what are calculated from the flux. of the reactor. So these are called the reactor anomalies. Then there are anomalies coming from experiments at Fermilab, which have to do also with properties of neutrinos at higher energies. So this of sterile neutrinos, as some of you may know, is at the moment one of the most active fields of research in particle physics, looking for these objects. And last summer, there was a meeting where I was participating at that, where it was decided the main research program of an accelerator called the Fermilab in Chicago, close to Chicago, Illinois, was going to be devoted mostly to the search for sterile neutrinos. So sterile neutrinos now are really becoming an important area of the research, and we have to understand whether they exist or not. Of course, the majority of people think that they are not there, they don't exist, but nonetheless, we are going to look for them. Why? Oh, Pontecorvo also. Pontecorvo did many things, also the neutrino oscillations and in '68. And no, he did not need it from the anomalies. He was suggesting that there could be additional neutrino species. He was asking the questions, why only 3 neutrinos? Even at that time, he did not know, because at that time, so Pontecorvo was an incredible person. It's a pity that we did not get much out of him because he was in the Soviet Union and was completely cut off from communication. So sterile neutrinos. So what we have done is we have calculated what is the effect of sterile neutrinos on double beta decay. And so we can do it in the same way. So what we are going to do is now give to neutrinos a mass mn, and then this form factor, this F function becomes mn over me. But the thing that changes is here the neutrino potential, because if now the neutrino is a mass which is not very small or very large, then one has to modify the expression for this potential, because now is the intermediate range interaction. And especially if Mn is of the order of the Fermi momentum in the nucleus, which is about 100 MeV over C, then it's no longer possible to do a factorization of the half-life in terms of phase space factor, nuclear matrix event, and their function. And unfortunately, the physics beyond the standard model is entangled with the nuclear physics. And so we have to do the full calculation here. We cannot split it into phase space factors, nuclear matrix element, and F. Here they're all mixed up together, and we have to do the calculation together. So this is the most difficult calculation. Huh? I did it. We did it. Yes, I'm going to try to. Now, this formula applies for a single additional neutrino with mass Mn. But if we look at the product of F times V, which is written here, you can take the limits of this product for mass of the neutrino going to 0, and then we get back the result of before, because if you put Mn here equal to 0 compared to the momenta, you have the result of before that I've shown in scenario number 1. And if we take the mass of the neutrino very large, then we get the other product which we have seen before. So this is a generic formula which works for any mass of the neutrino. In the limit in which the mass is either 0 or very large, then this formula reduces to the 2 previous ones that I discussed previously. Okay, so are we still doing okay? Okay, so now we have done a brief summary of the theory of zero neutrino double electron emission. Now, very briefly, something about double positron emission and electron capture with positron emission. Here is an example, the nucleus of cadmium-106, which can decay to palladium-106 by emitting 2 positrons, or the atom of 106 cadmium, the nucleus can capture an electron from the atom and then emit a positron. This process is also called double charge exchange process. Okay. Now the theory for these processes is identical to that of zero neutrino beta minus. The half-lives are still given by that. So here nothing changes except that phase space factors are now different because they correspond to the emission of the 2 positron, or emission of a positron and electron capture. So that's the only difference. So going from zero neutrino double electron to zero neutrino double positron, it involves essentially no change except for the phase space factors. So this poses no problem. Now, very briefly instead, I wanted to tell you about something that also been proposed, which is double electron capture with non-neutrinos. But if you have double electron capture with non-neutrinos like this, how can you conserve energy momentum? You cannot. So, this process in general cannot occur because it violates energy momentum conservation. The only way that it can occur is if the energy of the initial state is precisely equal to the energy of the final state. And so this is called resonant double electron capture. So this is a very, very rare thing to occur. And you can never have precisely the same energy. And so if you look at the width of the final state, it could be that the energy of the initial state is not so far away, it's within the width of the final state, and then the process could still occur. So what we need to do is do a very elaborate atomic physics calculation to calculate the width of the final state's gamma and also the location of where that state is. And then in this case, the half-life can be factorized into a phase space factor, the nuclear matrix length, the F function, and this resonant condition here, where delta is called the degeneracy parameter, which depends on the Q value for the reaction for this decay, the energy of the 2 holes in the daughter atom, not nucleus, and the width of the 2 hole states in the daughter atom. So this process heavily relies on atomic physics calculation and on nuclear physics. So very, very complicated thing to do, which we have done. Okay, but now before we proceed further, we still have to say a few words about 2 neutrinos double beta. This 2 neutrino double beta, it turns out to be more complicated than 0 neutrino. And the reason is that the neutrino momentum, in this case, is a few MeV, which is of the same order of magnitude of the energy levels in the intermediate nucleus. So the closure approximation cannot be used for this case, and we need to do an explicit calculation for going into each individual state and then sum over them. So we need to calculate the structure of all the nucleus and then calculate the matrix element for Gamow-Taylor Fermi, going from initial to the intermediate, from the intermediate to the final. This is a daunting calculation, and it has been done only in very, very few cases. The nuclear physics is overwhelming here. It's not easy at all. So only in 2 cases this separation can be done in the closure approximation, but also in a case in which there is only one single state that dominates, which is called the single state dominance, in which in both cases then this can be separated and one can do. And then we can do the calculation in the same way as we did the zero neutrino, except that we change the neutrino potential, and now this is the form of the neutrino potential in momentum space, and this is the Fourier-Purcell transform of B1. So I'm going to summarize, because today we are going to do a shorter lecture. So I'm going to summarize. Oh, still have time, so still going to summarize here the situation. So essentially what I've done in this lecture, I've told you of various possible mechanisms for this process, both for light exchange, heavy neutrino exchange, 2 neutrino Majorana emission, and sterile neutrino exchange. And within the formalism that I've indicated to you, all calculations can be done simultaneously by just changing the neutrino potential. So for light neutrino, the neutrino potential is long range, so the neutrino is emitted at one end of the nucleus and reabsorbed at the other end. For heavy neutrino, is very short range, so the neutrino is emitted here and immediately reabsorbed. For 2 neutrinos, the processes are uncorrelated, and so electron neutrino is emitted here, electron neutrino is emitted at some other place, and therefore we have that. And then I have discussed briefly Majorana emission, which is for the long range light neutrinos, where a Majorana particle is emitted here on the way between the emission and the absorption of the neutrino. And finally, I have talked a little bit about sterile neutrinos with mass intermediate between light and heavy. And let's see, good. And so this has been the introductory lecture. I want to leave some time for questions, if you have questions. And what the plan for this lecture is now that tomorrow I'm going to discuss the calculation of the nuclear matrix elements which appear in the process. Then in lecture number 3, I'm going to discuss the atomic physics calculation for the phase space factors. And then in second part of lecture number 3, I'm going to put everything together, phase space factors, nuclear matrix element, F function, and provide to you current limits on neutrino masses and where we are at the moment. Especially this last lecture will be important because INFN is very much involved in Cuore experiment and also in Gerda. These are 2 experiments going on at the Gran Sasso. One is an experiment that makes use of tellurium as a material, and the first result for the Cuore 0 have already been published, but now, if I understand correctly, all detectors have been assembled, and so Cuore will start taking data in the course of 2016, and we'll have some results by maybe a year and a half from now, where we'll begin to see the contribution of Cuore. So the calculation in tellurium is extremely important for Cuore. Gerda is another experiment going on at the Gran Sasso. This is in germanium, And there's a collaboration Germany, Italy, and so many Italian groups are involved also in GERDA, especially Padova, Bettini and others are involved in GERDA. GERDA has completed the phase 1 and is preparing phase 2. So GERDA will have results from phase 2 in a few years. And so INFN is very much involved in this. And also INFN now is getting involved in the sterile neutrinos at Fermilab. So this is also for importance to INFN for this for understanding the nature of neutrinos. And to conclude, neutrinos are one of the main areas of research at the moment in particle physics, in nuclear physics, as you've seen, and so they occupy a very important role, especially understanding neutrino-less double decay is crucial for understanding whatever physics is beyond the standard model, in particular in the neutrino sector, which is the one that was least known in recent years. Thank you.
Aside from proving or disproving with first of all, it's difficult even to prove or disprove with nuclear physical activation because there are no experimental data. But independent of this, I mean, which of these scenarios are more probable, more likely to be more realistic?
Okay. The only scenario which is should be there no matter what is the scenario with 3 light neutrinos with masses that are within the range that I have indicated there in the Vissani-Strumia plot. This has to be there because we have seen it in neutrino oscillations. Neutrino oscillations have proven that they have a mass, and so that part has to be there. The 3 neutrinos have to be there. For the rest, it's all a speculation at this stage. And in my last lecture, I will try to give my personal view of what may happen. But this, at the moment, is purely speculation. And if I have to put some money into it, maybe this idea of sterile neutrinos maybe after all may not be so strange. But they're pure speculation at the moment. Perhaps one more neutrinos, because when we have the bound from cosmology, the bound from cosmology is very strict on the number of neutrinos. So either you believe that bound from cosmology or you don't. Now cosmology is going to improve in the calculation because one criticism to the cosmology bound is that it comes from the result of a fit with, I don't know, many 24 parameters. And so if you tweak a little bit one of the parameters, you may have a problem in the neutrino mass. Although the claim is that this is not the case. So that is, the other is the result from, if we have results from Kachin, which is another important aspect where there the mass will be measured directly. But there again there are problems, and maybe I will discuss those problems later. And then there is an experiment going on here in Italy on electron capture on holmium-163, looking at the end spectrum of electron capture on holmium-163. This is Pallavicini and company. But then again, it's going to be extremely difficult to measure. When we thought that the mass of neutrino was electron volts, then okay. But if it's now we are going down to a very tiny fraction of electron volt, it's going to be very, very difficult to find it. And I will try to put some bounds, some limits in the next few lectures. Other questions? Some questions from the students, if there are students? Okay. Tomorrow, what time is it tomorrow?